Learning the proofs behind key theorems helps students understand the why behind math, not just the how. Proofs teach critical thinking, logical reasoning, and problem-solving skills, all of which are essential in math and beyond. In this video, we'll cover 10 essential direct proofs that every high school student should know, highlighting the principles that form the foundation of math. Must-know proof number 1, the proof of the Pythagorean Theorem. Let's say we have some right-angle triangle, where I'll label the shorter two sides of the triangle, side A and side B, and the hypotenuse, which is the longest side, I'll label it side C. And I'll also label the two interior acute angles of this triangle. I'll label the top left angle, I'll call it theta 1, and the bottom right angle, I'll call it theta 2. Now, most of my high school math students would be able to tell me the rule that shows the relationship between the length of the three sides of this right triangle. The Pythagorean theorem states that the sum of the squares of the shorter two sides, so a squared plus b squared, is equal to the square of the longest side, so equal to c squared. But do you know why this is true? Why, for any right-angle triangle, if I add the squares of the shorter two sides, do I get the square of the longest side? Let me give you a really nice, simple geometric proof that shows that relationship. I'll start by making a few copies of this triangle and positioning them in a way so that they form a square. Now that I've constructed this square, where all four side lengths are a plus b, I'm going to show you the proof of Pythagorean theorem by coming up with two equivalent but different ways of expressing the total area of this shape. Well, first off, to find the area of any rectangle, you just do its base times its height. And in this case, the base is a plus b and the height is also a plus b. So its area would just be a plus b times another a plus b, which I could write as a plus b squared, but I'm going to expand it, so I'll leave it in that format. And now I'm going to set this equal to a different but equivalent expression for the area of this square. I'll think of this square as a composite shape. It's made up of 1, 2, 3, 4 identical right triangles, and then also this square that's inscribed inside. So it's made up of 5 shapes. If I add the areas of all 5 of those shapes, that would give me an expression for the total area of this bigger square. Let me start by finding the area of this triangle in the bottom left. To find the area of any triangle, I just do half times the base times the height. So I would just do half times b times a. And don't forget, there are 4 of these identical triangles that make up my composite shape. So I can just multiply that half times b times a. I can multiply it by 4. And that would give me the area of all 4 of those triangles, but what I'm missing is the area of this square that's inscribed inside. Well, how do I know that this is a square inside? I can see that all 4 side lengths are c, but for it to be a square, all of the angles have to be 90 degrees. Well, this angle here is 90 because I know theta 1 and theta 2 have to add to 90 because the sum of the angles inside of any triangle have to be 180, meaning this theta 1 and theta 2 add to 90, and because these 3 angles, 1, 2, and 3, form a straight line, I know that this angle right here has to be 90. So this shape inside is a square, and I can find its area just by doing its base times its height, c times c, which is c squared. So I just have to add the area of that interior square, which is c squared. And now both the left and right side of this equation give me the total area of the big square. If I simplify both sides, it'll reveal to you the Pythagorean theorem. On the left, let me expand it by doing all 4 multiplications, and I get a squared plus 2ab plus b squared. And on the right, I have 4 times a half, which is 2, so I have 2ba, which I'll write as 2ab. And then notice on both sides of the equation, I have 2ab. So I could just subtract 2ab from both sides, which makes on the left the 2ab's cancel and on the right the 2ab's cancel, leaving me with, on the left side, a squared plus b squared, and on the right side of the equation is c squared, which is the Pythagorean theorem. Must know proof number 2, the proof of the quadratic formula. This formula is probably the most used formula in high school math. The formula is used to find the values of x that make a standard form quadratic equal to 0. Being able to use the formula is important, but it's more important to understand why this formula gives the solutions for this equation. Let me take you through a quick direct proof that will derive this formula for you. I'll start by moving this constant c to the other side of the equation, and then I'll solve this equation by completing the square. When completing the square, the first thing I should do is common factor this a from these two terms. And then what I want to do inside the brackets is to create a perfect square trinomial. To do that, I'm going to have to add and subtract a very specific value. The number that I add and subtract to create my perfect square trinomial is always going to be half of the coefficient of x squared. So I need to add and subtract b squared over 4a squared. Now I don't actually want this negative b squared over 4a squared, so I'm going to remove it from the brackets by multiplying it by the a that's in front of the brackets. Now what's left inside the brackets is what we call a perfect square trinomial. It's a perfect square trinomial because the first term is a perfect square, the last term is a perfect square, and the middle term is 2 times the square roots of the first and last terms. When you have a perfect square trinomial, it factors really nicely. It's going to factor to a binomial squared. Now the first term of the binomial is going to be the square root of x squared, which is x, plus the second term of the binomial is going to be the square root of b squared over 4a squared, which is just b over 2a. And now to continue the proof, I'll take this term, move it to the right, and I can actually combine these terms together by getting a common denominator. Right now this c is a c over 1, so if I multiply it by 4a top and bottom, it becomes 4ac over 4a. And now that I have a common denominator, I can write that as a single fraction. And now I'll continue this proof over here. On my next line, I'm going to divide the a to the other side. And keep in mind, my goal is to try and isolate x, so I need to get rid of this square. The inverse of squaring is plus or minus the square root. Now when square rooting a fraction, the numerator needs to be square rooted and the denominator. The square root of 4a squared is just 2a, so I can simplify that. And then lastly, just subtract this term to the other side. And because they have a common denominator, they can be combined into a single fraction. And there we have it, the quadratic formula, which finds the solutions to a standard form quadratic set equal to 0. Must know proof number 3, the proof of the sine law. Let's say we have some oblique triangle, triangle ABC. In this triangle, I've labeled the angles with capital letters, and the side lengths will be with lowercase letters. The sine law states a relationship between the sides and angles in any triangle. The sine law states that the ratio of any of the three sides of the triangle divided by sine of its opposite angle would be equal. So a divided by sine a would be equal to b divided by sine b, which would be equal to c divided by sine c. Let me give you a proof of how we know that this relationship holds true for any triangle. Let me start by making a few copies of the triangle. And then in these two triangles, let me draw an altitude from vertex A. That means a line that goes from A to the opposite side and forms a 90-degree angle with the opposite side. And I'll call the point that it connects to the opposite side at, I'll call that point, point D. And let me label these altitudes as the height of the triangle. Now in this leftmost triangle, let's start by looking at the triangle ABD. In this triangle, based on SOHCAHTOA, I know that sine of angle B would equal its opposite side, h, divided by the hypotenuse, c. And then isolating for h, I can multiply both sides by c to find out that h is equal to c multiplied by sine b. And now in this triangle, let's focus on the triangle ACD. And now since these two triangles that we're looking at, they both have the same height, they both have this side in common, I'm going to come up with a different but equivalent expression from this triangle for the height. What I'll do is I'll say that sine of c is equal to the opposite, h, divided by the hypotenuse, b. And then isolating for h by multiplying both sides by b, I would figure out h is equal to b times sine of angle c. In these two equations, I see two different expressions for what h is equal to. H is equal to c sine b and also b sine c, which would mean that c sine b would have to be equal to b sine c. Since they're both equal to h, they have to be equal to each other. And then to this equation, I could divide both sides by sine b and sine c. And then after canceling, I see that c over sine c is equal to b divided by sine b. And then if I went through this same process, but drew the altitude from one of the other two vertices, either from C or from B, I would be able to show that each of these ratios are equal to A over sine A. And that's the proof of the sine law. Must know proof number 4, the proof of the cosine law. Let's say we have some triangle ABC. The rule for the cosine law states that the length of any of the sides of this triangle squared, so I'll pick side A, meaning A squared, would be equal to the sum of the squares of the other two sides of the triangle, B squared plus C squared, minus 2 times the product of those sides B and C, multiplied by cosine of the angle contained by those sides B and C, means the angle between B and C, which is angle A. So I have to multiply this by cosine of angle A. Now this formula is often used to find the measure of side A when you know the length of the other two sides and the measure of the angle contained by those two sides. But why are we allowed to use this formula? Why does this formula work? Let me give you a nice proof. Let me start by drawing an altitude from C, and I'll call this point where it connects to the opposite side, I'll call it point D. Notice I have created two right triangles, one on the left and one on the right. Let's start by looking at triangle ACD that's on the left. Now in this triangle, I don't know the measure of this bottom side, side AD, so I'm just going to say it has a length of x. And then using SOHCAHTOA, I know that cosine of A would equal the adjacent side, x, divided by the hypotenuse, b. And isolating x by multiplying both sides by b, I would find out that x is equal to b times cosine of A. And then I'm going to make another equation with this triangle. I'm actually going to call this side the altitude. I'm going to call it the height of the triangle. And then because it is a right angle triangle, I know Pythagorean Theorem is true, which tells me the sum of the squares of the shorter two sides, so x squared plus h squared, must be equal to the square of the longest side, the hypotenuse, so b squared. Now let's move on to this right triangle, the one outlined in blue. I'm going to write an expression for the bottom side. Since I know from A to B is length c, and since A to D is length x, I know that this side from D to B must be the difference between c and x. And then because this is a right angle triangle, I know Pythagorean Theorem is true, which tells me the sum of the squares of the shorter two sides is equal to the square of the longer side. And then expanding c minus x squared gives me c squared minus 2cx plus x squared. And then a couple things I notice. I have an x squared plus an h squared, which I know from the other triangle is equal to b squared. So I can replace it with b squared. And then also I have this x, which I know is equal to b cos A. So I can replace that x with b cos A. And then just with a little bit of rearranging, this will look like the cosine law formula that you're used to seeing. And there you have the cosine law. Must know proof number 5, the proof for the formula of an arithmetic series. As a quick reminder, an arithmetic series is just a sum of a bunch of terms from an arithmetic sequence. And that would look like this. Notice there is a common difference between all of the terms that are being added together. In this example, the common difference between each term in this series is 3. That's what makes this an arithmetic series. Now let's say you wanted to find the sum of the first 40 terms of this series. Instead of adding them all together, you could use the arithmetic series formula. To find the sum of the first n terms in the arithmetic series, you just do n divided by 2 multiplied by 2a plus n minus 1 times d, where n is the number of terms in the series, a is the value of the first term, and d is the common difference between the terms. Let me show you why that formula works. Now to start off with, you need to know the formula for the general term of an arithmetic sequence. To find the value of any one term, not the sum of the terms, but just the value of one single term, you just take the first term a and add the common difference n minus 1 times. So that would mean that if we're finding the sum of n terms in any arithmetic sequence, we would just take our first term, which we call a, and then we would have to add our second term to that. And then using this formula to get the value of the second term, if I sub 2 in for these n's, this would simplify to a plus 2 minus 1 times d, which is just a plus d. So my second term is just a plus 1d. And then to that, I would add the third term in the series. And then to find the third term in the series, I would just replace these n's with 3, making this simplify to a plus 2d. And you could probably see what's happening. We have an a plus 0d, then the next term is a plus 1d, then term 3 is a plus 2d, and this is just going to keep on continuing until we get to our last term, where for finding the sum of n terms, the nth term would just be equal to a plus n minus 1 times d. Now let me actually space these terms out a little bit, because I'm going to write the formula for the sum of the terms in any arithmetic series in a different way. I don't have to add the terms in this exact order. It doesn't have to be the first plus the second plus the third all the way down to plus the last. I could add them in any order, including in reverse order. Why don't I start with the last term of the arithmetic series? And then I need to figure out what would the terms look like as I go back through this list from the last term all the way to the first term. Well, when I went in this direction from first to last, the coefficients of d, it went from 0d to 1d to 2d, and it would go 3, 4, 5, all the way until it got up to 1 less than n, being as the coefficient of d. So when going the other way, instead of the coefficients of d increasing by 1 each time, they're going to decrease by 1 each time. So what's 1 less than n minus 1? Well, that's n minus 2. And then the third last term in the series would be a plus n minus 3 times d. And this would keep going all the way until I got to the first term that's in the arithmetic series, which is just a. And now what I'm going to do is I'm going to add these two equations together. On the left side, I have Sn plus Sn, which is 2Sn. And then on the right side of the equation, when I start adding my terms that are in columns, in the first column, I've got an a plus n minus 1 times d. Well, I can collect the a's together. They're like terms. That gives me 2a. So I would have 2a plus n minus 1 times d. Plus, looking at the second column, when I add those terms together, a plus a is again 2a, plus 1d plus n minus 2 times d. Those are like terms. They both have this variable d. So I can just add their coefficients. 1 plus n minus 2, that's n minus 1. So I have n minus 1d. Notice the sum of these two terms was the exact same as the sum of those two. And that's going to happen for each pair of terms. They're always going to add up to 2a plus n minus 1 times d. And in the arithmetic series, how many terms do I have here? How many total terms are there? Well, I'm finding the sum of n terms. So there are n terms here, and they're all the same. So instead of adding them all together, I could just multiply one of them by n. And then lastly, just divide both sides of the equation by this 2. And that will give me the final formula for the sum of n terms in an arithmetic series. It's just n over 2 multiplied by 2a plus n minus 1 times d. Must know proof number 6. Let me give you a geometric proof for the difference of squares formula. You're probably familiar with the rule that states that a squared minus b squared, a difference of two squares, is equal to the product of a minus b multiplied by a plus b. Now, algebraically, it's easy to prove these are equal just by expanding the right side. You would see that it's equal to a squared minus b squared. But let me give you a nice geometric proof as to why these two expressions are equal to each other. Let me start by constructing a shape that will show you a squared minus b squared. So I'll draw a square with side length a, and this square would have an area of a squared. But I want to construct a squared minus b squared. So I'm going to cut a square out of the bottom corner here, where this square is going to have side length b. So that leaves me with this shape, which I'm outlining here. Its area is equal to the area of the big square, a squared, minus the area of this cutout, which is b squared. So its total area is equal to a squared minus b squared. And now let me show you a different way I could reconstruct this shape as a composite shape so that I could get a different but equivalent expression for its area. What I'm going to do now is divide this into a composite shape by drawing a line right here which divides it into two different rectangles. And keep in mind, this side is still side A, but what are the other dimensions? This side down here, notice, matches this, which is a side of this square where all the sides are B. And then the bottom side of this rectangle matches this side over here, which is not equal to A. It is B less than A, so I could label it as A minus B. And in rectangles, opposite sides are equal, so I'm just going to move that A minus B to the top of that white rectangle. And then this side here matches this side, which once again would be A minus this B that's been cut out. And then by taking this green rectangle and moving it down here and rotating it so it fits nicely, you'll see a really nice proof of this difference of squares formula. I'm going to have to make a bit of room, and then I'm going to copy the diagram and show you moving that green rectangle. If I bring it down and rotate it, it'll fit exactly forming this new rectangle, where notice the top and bottom are both A minus B, and the left and right are both A plus B. And then since this shape and this shape have equal areas, I could set them equal to each other. This area is A squared minus B squared, and that must be equal to the area of this rectangle, which is A minus B times A plus B. And there you have the difference of squares formula. Must know proof number 7, the power rule of logarithms. This rule states that if you have log base b of some power x to the power of n, that's equivalent to, you're allowed to take the exponent on the argument and write it as the coefficient of the logarithm. So it's equal to n times log base b of x. That's a nice, easy rule to use, but do you understand why it works? Let me show you a proof. And actually, before showing you the proof, I should state the restrictions on the base of the logarithm and on its argument. The base always has to be a number greater than 0, and it can't be 1. And the argument, x, has to be greater than 0. All right, now let me take you through the proof of why we're allowed to use this rule, why we're allowed to take this exponent and write it down as the coefficient of the logarithm. Let's start by letting w equal log base b of x. If I convert this equation into exponential form, I know that w is the exponent that goes on b to get x. So in exponential form, it would be b to the power of w equals x. And notice in the rule, the argument of the logarithm is x to the power of n. And in the equation I have down here, it's just x. So what I'm going to do is actually raise it to the power of n, which I can do as long as I raise the other side of the equation to the power of n as well. And then on the left, when you have an exponent on top of an exponent, you multiply them together. And now what I'm going to do is convert this exponential equation back into logarithmic form. I know the exponent on b will be the answer to the logarithm, the base of the power is going to become the base of the log, and the answer to the power becomes the argument of the logarithm. So the argument is x to the power of n. And then lastly, on the left side of the equation, I have a w, which we know is equal to log base b of x. So I'll substitute in log base b of x for w. And I'll actually write the factor of n first so that it matches our rule. So we have n log base b of x equals log base b of x to the power of n, which is exactly equal to our power rule of logarithms. Must know proof number 8, the product rule of logarithms. For this rule, if you have two logarithmic expressions being added that have the same base, so log base b of m plus log base b of n, what you're allowed to do is write it as a single logarithm by keeping that same base of b and then multiplying the arguments together. So multiplying m and n together becomes the new argument of our single logarithm. That's the product rule of logs. And remember, for any logarithmic expression, the base has to be greater than 0 and not 1, and the arguments have to be greater than 0. Let's get the deeper understanding of why this works. Let me show you the proof. These two log expressions, I'm going to set them separately equal to x and y. And how I'm actually going to prove this rule is by converting both of these equations into exponential form and then using the exponent rules that we know are true. So let me convert both of these to exponential form. The first one, I know that b to the power of x must equal m. And in the second equation, b to the power of y equals n. And because I'm trying to prove the product rule, it's actually going to work out if I make an equation that involves the products of both sides of these equations. So if I do the product of b to the power of x times b to the power of y, I know that would be equal to m times n. And I know that's true because b to the power of x is equal to m from that equation, and b to the power of y is equal to n from this equation. And then on the left side of this equation, the reason I set this up as a product of powers is because I know when multiplying powers with the same base, we can keep the base the same and add the exponents. And then I'm going to convert this back into logarithmic form. The exponent becomes the answer to the logarithm, the base of the power becomes the base of the logarithm, and what the power is equal to becomes the argument of the logarithm. And the last thing I have to do is replace x with log base b of m and replace y with log base b of n. And there I have the product rule of logarithms. Must know proof number 9, the power rule of derivatives. The rule states that if you're finding the derivative with respect to x of x to the power of n, where n is any real number, that's equal to n multiplied by x to the power of n minus 1. You just take the exponent, write it as the coefficient of the power, and then reduce the exponent by 1. But why are we allowed to use this rule? Let me use Newton's quotient to do this proof. If I'm trying to find the derivative of a power function, x to the power of n, I know that would be equal to, based on Newton's quotient, the limit, as h goes to 0, of the function at x plus h, so x plus h to the power of n, minus this exact function, all over h. This is just my change in y over my change in x, where the change in x is approaching 0. And now somehow, this limit needs to simplify to just n times x to the power of n minus 1. Let me show you how that happens. We need to actually expand the numerator. Well, how are we going to expand this binomial that has an exponent of n on it? We're going to need the binomial theorem. In the expansion of a plus b to the power of n, you can find any one individual term. You can find term r plus 1 by doing n choose r times a to the power of n minus r times b to the power of r. Let me just move this over so we have a bit more room, and then let's go ahead and try and use this formula to find a bunch of the terms when we expand that binomial. Well, in the expansion of this binomial, the first term, I would have to sub 0 in for r into this equation. And the exponent on the power is just n, and instead of a and b, we'll be writing x and h. So the first term would be n choose 0, x to the n minus 0, which is just n, and then h to the 0. Plus, then if I want the second term, it would be n choose 1, x to the n minus 1, h to the 1. And then if I want the third term in the expansion, it's n choose 2, x to the n minus 2, h to the 2. And then this expansion is going to keep on going until we get to n choose n, x to the n minus n, which is 0, h to the n. And remember, this is just the expansion of that binomial. We still have to subtract x to the power of n. So let me make a little bit of room here for that minus x to the power of n. And then let me simplify things a little bit. N choose 0 is just 1, and h to the 0 is just 1. So my first term in the expansion of the binomial is just x to the power of n, which then just cancels with that last term we're subtracting. X to the n minus x to the n is 0. And then of all the terms that would be left in the expansion, notice all of them have at least one power of h. So what we could do in the numerator is we could common factor out an h. When this first term gets divided by h, the h is gone, and then I'm left with n choose 1, which is just n, times x to the power of n minus 1. And then the second term, I'm left with n choose 2 times x to the power of n minus 2, and then one of those two factors of h will be gone. And then this last term, n choose n is 1, x to the 0 is 1, so we're just left with h to the n, but I've common factored out at h. H to the n divided by h is h to the n minus 1. And then because we're finding the limit as h approaches 0, I'm able to cancel out those factors of h and be left with an equivalent limit statement. And now I can do direct substitution where I actually set the h's equal to 0. Well, all of the terms, except for the first one, have a factor of h. So when I sub in 0 for h, all of the other terms, except for the first term, are going to be gone, leaving me just with n times x to the power of n minus 1. Must know proof number 10, the product rule of derivatives. The rule states that when finding the derivative of a product of functions, let's say the derivative of f of x times g of x, the product rule says that's equal to the derivative of the first function of x, f prime of x, times the second function, plus the derivative of the second function, g prime of x, times the first function. And let me show you why we're allowed to use this derivative rule, once again using Newton's quotient. Based on Newton's quotient, I know the derivative of the product of functions of x will be equal to the limit as h goes to 0 of this product of functions at x plus h minus the product of those functions. And that's all over h. And actually, to be able to prove the product rule, to be able to create these derivatives within this expression, I'm actually going to have to add in a term. I'm going to subtract f at x plus h times g of x in the numerator, which I can do as long as I also add it. Notice what I wrote in green here is actually just 0, so I haven't changed the value at all. And what I'm going to do now is factor by grouping. In the numerator, I'm going to look at the first two terms and common factor out an f at x plus h from both terms. And then the last two terms, I can factor out g of x. And then I'm going to separate this into two fractions. And based on limit rules, I know I'll be able to find the limit of both of those fractions as h goes to 0. And then let's evaluate these limits. The limit as h goes to 0 of f at x plus h, well, as h goes to 0, f at x plus h goes to f at x. And then notice the limit as h goes to 0 of this fraction, g of x plus h minus g of x over h, that's just the definition of a derivative. That's the definition of the derivative of g of x. So that's g prime of x. Plus the limit as h goes to 0 of g of x. Well, as h goes to 0, g of x is still just g of x. But as h goes to 0, f at x plus h minus f at x over h, that's the definition of a derivative based on Newton's quotient. So I can write that as the derivative of f at x, which is f prime of x. And then just with a little bit of rearranging of those terms, you would see that this is exactly equal to the product rule of derivatives. So hopefully if you made it to the end of this video, you have a better understanding of all of these rules you use in high school math. Let me know in the comments what you want a top 10 of next. Jensen Math!